Well, thank you very much for the introduction and thank you for the invitation. I'm very glad to be here to give this talk today. So with respect to the presentation, this would be something that kind of nothing to do with what I'm used to do. So it is about the microlocal analysis of singular measure. And it is a joint work with Nicola Burke with in Orsay. Okay. So let's see, the plan of the talk is the following. First, I will present the framework of, the question we are looking at. And then this will be the main contribution. We'll define a wavefront for distribution, but at the L1 regularity, right? We used to Hormander's wavefront set for safety regularity, for instance, but in here we'll talk about L1 regularity. And then based on this definition, I will give a main result and several of its consequences. And just to give you an idea, an example of application, in case if you're interested or not on this topic. So a typical consequence of these results are that if, for instance, the Laplacian of a distribution is, well, forget for a moment of this sign here, is in L1 log, then it is well known that in general you don't recover all the second derivative in L1. But however, if we'll impose the extra condition that the second derivatives are radon measured, temperature radon measures, then we will recover the full L1 regularity for the whole range of second derivative of the distribution. Okay, so what's this sign? And well, this is done usually, you don't recover all the L1 regularity, because if you write this distribution in terms of this distribution, you will end up with a pseudo-differential operator of order 0 that's acting on L1, right? And this we know that it's not continuous. Okay, so I will present rapidly what are pseudo-differential operators in general, but just to, since already in the statement and in the proof, zero-order pseudo-differential operator will appear. Let me also underline that they are not artificial, that they also appear naturally in harmonic analysis and PDEs. As famous examples are Hilbert and Ritz transform, and starting from them, other operators that come into application, like the ray projectors or Biot-Savart operators. Okay, so now what is the framework? So the framework is that if you consider a locally bounded measure, well, you can decompose it with respect to its total mass measure. It is the polarization, the composition, and then you can decompose its total variation measure with respect to the Lebesgue measure, and end up with this kind of decomposition where you use twice radon nicodym zero. Okay, so this is the singular part of the measure, and now what we know is this very nice result of the Philippines and Rindels that go back to 2016. Which says that if you have a constant coefficient operator of order k, then if in the sense of distribution, A constrains the measure to cancel, then mu is almost everywhere. So roughly on the singular part of the measure, the polarization function lies in this set. Okay, so reunion of the kernels of these functions that actually you already might notice that these are the principal symbol of these operators. Okay, so a few comments about this result. That is why I'm saying it's relevant for systems and non-elliptic constraints, is that, for instance, if you think about the scalar case, if you have a non-elliptic constraint, this means that this set fills the whole space R. So this doesn't say anything to you. Okay, and in general, scalar or system in for elliptic constraints, if the operator is of order 0, this means that it's just a constant coefficient matrix, then you can invert it, and of course, even here you have L1, you end up with L1. Okay, so you get the fact that your measure is absolutely continuous with respect to the Lebesgue measure. Okay, and if the operator is of order strictly larger than 0, then since we said that if it is elliptic, then you can pick an inverse operator of it, and then when you apply it to the right-hand side, even if here you have some L1 function, then as the inverse operator is of orders minus k, with k different from 0, positive. So this is a regularizing operator, and you end up with having mu in L1. Okay, so this theorem is relevant for a system and non-elliptic constraints. And what it does is that connect the singular part, the polarization on the singular part, with the Murat-Tartar wave cone of non-elliptic direction of the operators. So as I've said previously, this function here is the principal symbol of this operator, and having this lying in this kind of kernel of the principal symbol of an operator, meaning that you are in the characteristic set of the operator, and this calls for a property of wavefront type. Okay, so this is precisely what we'll do. We'll look for a wave front notion. So before that, I need to introduce pseudo-differential operators. So it's you can see them as a generalization of ordinary differential operators, where if you write them in Fourier, for instance, one derivative will mean that you multiply in here by xi simply. And in here, it's a generalization with the symbol A being in some classes having some appropriate decay properties. Okay, and we consider that the principal symbol that we consider operator, classical operator that have homogeneous principal symbol, meaning that outside the neighborhood of the origin, the principal, you are modulo a symbol of lower order, you are homogeneous of degree k. And this is the function you define as the principal symbol. Okay, well, for instance, for the Laplacian is xi square, modulus of xi. Okay, so here is the definition of the wavefront set. So what is the wavefront set? In here, we define it for general temperate distribution. So it will be, unlike we are used from Hormander's set for scalar distribution, it will be a subset where you'll have a localization in space, in frequency, and also in polarization, in values, if you want. Okay, if you go to values in Rm, the wavefront will be triplets. Okay, so as usual, you can define it maybe easily by saying what does it mean if you are not in the wavefront. Well, a triplet is not in the wavefront if at this location you can find an elliptic operator that constrains your distribution to end up at the regularity you want. So for us, it will be to end up in L1, and well, we add also some pseudo differential operator of there's 0 in front to fit with how it works. Okay, so this is the definition. So elliptic in this sense now, that of course, if you are in the scalar case, boils down to the usual elliptic definition of an operator. So an elliptic constraint that that brings your distribution into L1 at that point. Okay, so this is exactly, I mean, the same kind of definition as Hormander wavefront set is from the same infinity regularity. And also this was for scalar distribution, and you have a generalization due to Denker to vectorial distribution, which is precisely in this spirit. Okay, these are some few properties of this set. It is closed, conical, linear in omega without taking 0. And if you have a function distribution that is L1, then its wavefront set is empty. Why is that? Is because roughly you can take the identity in here, and you end up that all triplets lie outside the wavefront set. Okay, and well, this is just to give you an example of what can wavefront set be. For instance, is if you take a Dirac mass and you multiply it with some vector, then the wavefront set will be as for scalar ones, and as for the polarization coordinate, you put all the direction collinears, I mean, all the vectors collinear to omega 0. Okay, so now, of course, well, okay, we have defined the set, so what? We want some properties about this set. Usually what you want from a wavefront set is to capture precisely the regularity you want. Typically, you want the inverse implication here. If the wavefront set is null, you want your distribution to be in L1. But these kind of things are not possible in L1. You cannot hope as in the same infinity setting for a statement like precisely if your wavefront set is empty, then you are everywhere at a good regularity. And also this kind of elliptic estimate, that's, well, all of them are kind of the same in some sense. Okay, and this is simply because the zero order, so the differential operator do not act continuously from L1 to L1. Okay, and this just to give a counter example. You have this counterexample that you can find in Giacinta Martinazzi or Giudetti Unesu and Palara of a distribution that is in L1, derivative in L1, and then you have indeed the Laplacian in L1 of the ball of the plane in dimension 2. But however, if you look at the full set of second derivative, you are not in L1. And the remark you have to do in here is that if you look at precisely what are all the second derivative, you end up that this is not a Radal measure. Okay, so now comes our main theorem, which restricts now the study of this wavefront set from distributions to Radal measure, to temperate Radal measure. And this result is a connection between both polarization and support of the singular part of a measure. And in here, the measure it is for general measure. So for instance, no constraint on the measure. You just take a temperate Radal measure, and this result ensures that mu is almost everywhere location and polarization lies in the projector on the first and third component of the wavefront set, meaning that almost all US, almost all point X, you might find xi such that the triple with X and polarization at X, first and third component lie in the wavefront set. And the proof is based on microlocal analysis technique, on all the developed Linder's approach, and also on some extra properties of tangent measures. Okay, so now again we want to get back to this wavefront set and be convinced that it's a good notion, and precisely this theorem allows you to have the desired feature of a wavefront set, that is to capture precisely the location where you have the regularity you're looking for. So typically now we have both implication between if the projection of the first component of the wavefront set is empty, then you're sure to be in L1 block, and well, the converse is also true, of course. And moreover, you are sure with this wavefront set to capture all the support of the singular part of the measure. Okay. Okay. So this shows that this wavefront set is a good characterization for this kind of regularity, L1 regularity for temperate measures. And as another type of consequence is that you have indeed a full L1 regularity elliptic result, meaning that if you take an elliptic operator, in the sense that its kernel is trivial, and this for all for frequencies, and you take a temperate measure, then if your elliptic operator constrains your measure to lie in zero pseudo order of zero pseudo-differential operator, it's easier to write it pseudo. Apply to function in L1, then you locally at the point x0 you are in L1. Okay, and then as sub-consequences of this consequence, you easily get typically the first the application I put on the first slide, meaning that if you have some operator that's elliptic, for instance, the Laplacian of second order, and you know that the derivatives of the order of the operator are all temperate measure, then you get the fact that if this elliptic operator constrains your measure to end up in psi 0 L1, then you're sure to earn all the derivative up to the order of the elliptic operator to be all in L1. Okay, and well, for instance, if you consider BV function, meaning that the gradient is a measure, then it means that if you have some elliptic operator that sends you the gradient in psi 0 L1, then you recover that your BV function is actually a W11 function. Okay, another example of sub-consequence is that, again, if you take U in BV, so that you have the gradient to be a temperate measure, and if you impose moreover that the divergence and the curl of U end up in psi 0 L1, then you can conclude similarly that the gradient is in L1 block by taking in the definition, for instance, if you want to see if the first derivative d1u lies in L1, then A applied to d1u, d1 commutes with d1 curl, then you'll end up with something which is of order 0 in here, d1 of some over something of order 1, so it's order 0 of the even curl of u that are in xi0 L1. So you are exactly in this setting, an elliptic operator applied to your measure, end up in xi0 L1, so your measure is in L1. Okay, so another consequence. Well, we end up also with an extension of the Felipe Strinder's result. So it is an extension to here you can take whatever you want as matrices, not only constant coefficient or variable next coefficient, but generally pseudodifferential operator of order k, and you can take them k larger or equal to 0 and put a constraint in the right hand side to be of type xik L1, and then you have the expected result that the polarization on the singular part of the measure lies in the characteristic set of your operator, meaning the kernel of intermeaning of the kernels of the principal symbol. Okay, and as I already said, in this more general framework, passing to 0 order, because in here you can have, of course, 0, 0 on both sides, is something non-trivial. Having the operator of the same order of what is on the right hand side is non-trivial. Okay, and this was a remark also done by the Felipe Strinder in their paper, is that if you can put on the right hand side some operator, but of strictly lower order than what's in the left hand side, and then you can put in here a measure, not necessarily L1, then you have the same kind of theorem. Okay, so let me give you the proof of this extension. So by using our main theorem, this means that disrespectful to any constraint mu satisfies, we know already where the polarization lies. Okay, so it lies on the x and its polarization lies in the projector on the first and third component of the wavefront set, which means that for mu_s all point x, you can find a frequency such that you have this triplet in the wavefront set. And the wavefront set, if you look at the definition, it is made by the triplets such that the last component belongs to the intersection of all the kernels, of the kernels of the principal symbols of all operator that constrain your distribution measure to end up in the desired regularity class, xi0 and 1. And now we use the hypothesis that tells you that, well, capital A is such an operator. Well, its k is larger than 0. If you want to get to xi0, you divide by an elliptic like 1 plus Laplacian to the power k over 2. Okay, and this doesn't change the principal symbol. Okay, so now A roughly is this kind of satisfy this kind of condition, so you immediately get that x and this triplet lie in the kernel of this. The third component, that is the polarization, lie in the kernel of AK. Okay, and this proof is so short because, well, this kind of show that the wavefront set is the natural notion to consider for this kind of results. Okay, so as a last consequence, well, In the Philippines-Rindrat paper, from their theorem, they got actually an impressive number of consequences, which of course part of them I don't understand because it's really out of my field. But well, we looked at some of them, and for instance, in their paper, they find another proof of Alberti's rank 1 theorem. And in here, with our theorem, we can generalize it in the sense that if you have a temperate measure whose curl end up in psi1 of L1, so pseudo-differential operator of order 1 applied to L1, then you are sure that the polarization is of type of rank 1 type. Okay, so in the case, if in this statement you take the particular case of gradient measures, so measures that are of type gradient of u, then immediately you get that curl of mu is 0. Okay, so Albert rank theorem is, if you look at it through this equation, is to end up in here to have just 0. While in here you can have, you can allow for constraint that even have one derivatives. Okay. Okay. So well, I went pretty fast. Sorry. Now I will get to the proof of the main theorem, and I will try to slow down a bit. Okay. So the main theorem states that if you start with the temperate random measure, then mu s almost everywhere, you're sure that x and the polarization at x end up in the first and third projection of the wavefront set. Okay, so you suppose that's not true. So you suppose a significant part of this kind of couples falls out of this projection of the wavefront set. And the aim will be to find such a point in this set where you will get some an elliptic constraint that will send you in roughly in L1. And then to invert and see, get to a contradiction. Okay. So now you are in this set. Then, as I said, we're looking for elliptic constraints. So this is quite natural from the definition. Outside the wavefront set is that you have elliptic constraint everywhere. Okay, they actually depend on the second variable, the frequency, but this is not an issue because the frequency are lying in the sphere, which is compact. So you can get a covering of this set by elliptic constraints that roughly are valid for all direction psi. Okay, so now there are first issue is that well, okay, now for all the points in here, I'm sure to have an elliptic constraint such that we're sent into psi 0 L1, which is precisely what we want, except that later in the proof we need some properties on the function on the right hand side on the three terms, which are valid mu s almost everywhere. Okay. So the issue is that if you pick a point in here, and if you want to have these properties, well, it might happen that this property is not valid precisely at the point x. You see, you have a point x, and for each point x, you have some functions. And this function have your extra desired properties, mu s almost everywhere. So it might be that it doesn't happen precisely at the point x, which is a pain, of course. So what to do? What to do is, well, you want to get this kind of elliptic constraint, not only pointwise, but on big pieces of the space, okay? So now, the issue now is that, well, of course, what concerns the space variable, of course, once you have this kind of condition, you can extend it in a small ball center, in a small neighborhood of x0, such that you still have this. Okay, so that's pretty nice, but still, eventually, you want this to happen from this kind of points. Okay, so you want to have as a third component the polarization at the point. So when I'm saying that this constraint, I mean this property, you can extend it in a neighborhood of x0, it will be, of course, still valid, but with respect to omega 0. Okay, so what we want is to be at x with respect to the polarization at x. Okay, which will be, of course, satisfied if we knew, for instance, that the polarization is a continuous function, which in general is not. But of course, it can be almost the case, and that's what we'll do. So we, to get good elliptic estimates, what you want is to take advantage of the fact that you have almost continuity for the polarization function in Lebesgue points sets with respect to this singular measure. Okay, so what you do? So already we set to each point x, we associate a small radius on which we are sure that the ellipticity condition holds well, with respect to the polarization at the center. Okay, and also if it is sure, it will still hold for direction not too far from the polarization at the center. Okay, so this is precisely what we'll do. We'll consider smaller radius at each point such that we are sure that the polarization stays close to the central one, at least for a part of the balls, which is pretty large with respect to the total mass of the ball. Also, we need to restrict the set A first to the compact set, because we'll use Betikovich theorem, and we need the set to be bounded. And then we also have to remove to reduce to the density point with respect to the measure, to be sure that at least for other small radius, the way you charge k intersection with the ball is similar to a big percentage of the size of a ball. And then with all these conditions, you use Bedikovich theorem to get a covering, a countable covering. And from this covering, you restrict now precisely to the sets where you know that you have a polarization that didn't deviate too much from the central one, from the one on the center of the ball. And since it doesn't deviate so much, we are sure that the elliptic constraint, now it is respect to polarization at each point. Remember now that if I take the elliptic constraint coming from the point xn, we have that sequences fxn that appear, and from which we should remove some null sets such that we have the good properties of f at xn. And eventually, we just have to show that after all, removing all these parts, we end up with a set of positive measure, which is roughly the case because we started with a set of positive measure, roughly. Okay, so now we have a good elliptic constraint at a point that falls out of the wave-prone set. And then we'll follow, once we have this elliptic constraint, the steps of the proofs, main steps are the same as for the Phillips-Rindel, and they are based on introducing a tangent measure, second due to price. And through this tangent measure, which means that you zoom your measure at a point x0, you do the pushback of your singular measure by a dilatation center in x0 and of coefficient rj for some sequence rj going to 0, and you normalize this measure. Then the results of price ensure you that you have a weak limit that tends to a scalar positive measure times the polarization precisely at the point you are doing the zoom. And you also have the fact that if you look at the zooms on the singular part only, on the singular part of the total variation measure, then you end up with the same measure in here. And also this measure is non-trivial, and you know also that the approximate measure are orthogonal to the Lebesgue measure. And you end up with a contradiction if you show that your tangent measure is in L1 in this set, and if or moreover you have convergence in measure for the difference of the sequence. So eventually, if you show this, you end up to a contradiction very quickly because of the fact that VJs are orthogonal to the Lebesgue measure, and the final distribution is in L1. Okay, so now the goal is to show this property, and to show this property, it is easy to see that if you smooth and localize the scalar measure mu g in the ball where everything is happening, it is enough to show that this sequence is precompact in L1. So how you do this? So you zoom, you started from a constraint, an elliptic constraint on mu, and you zoom it. Okay, so now with respect to the Phillips-Rindel proof, well, they do the same, they zoom, except that working with the constant coefficient, you don't see the zoom. After the zoom, your operator is still the same, while in here, as you're working with the pseudodifferential operators, the zoom influences your operator, and you end up with a family of operator, and you have to be careful to have uniform in J estimates for whatever you want to do in the following, and this is quite a pain. Okay, so you have to use several microlocal analysis tricks to be sure that you get properly the uniform in J estimate. Typically, you have to cut off low frequencies, but to cut off nicely low frequencies, you want to have a good symbol from the composition, and we end up using right quantization. Okay, so that's one series of issues coming from the fact that you are working with the pseudodifferential operators. And then, well, you localize, smooth, and invert the equation, the left-hand side, and you end up with an expression of uj. uj equals a bunch of terms involving lots of operators depending on j again, of course. And you want to prove precompactness for all of them. And to do so, well, you use classical results on differential operator acting on Sobolev spaces, and also some results on bounded measures. You also need to use L1 infinity estimate for zeroth or pseudodifferential operator, okay, which is the borderline. You don't have L1, but you have L1 infinity, L1 weak. And then also, typically, as said at some point, you localize in space. When you localize, you will end up with the commutators. Okay, so commutators applied to mu j. Okay, if you are a constant coefficient case, the commutator are local. Okay, so eventually you have some operator, actually of good order, applied to a localization time mu j, localization in space. And this, if you localize mu j in space, with the localization that doesn't depend on j, of course, then you have uniform in j estimate. While if you work with the pseudodifferential operators, well, the commutator of B and localization in space won't, it's not local. So eventually we need to prove also a temperate estimate on the mu j, the sequences of zoom measure that converge with it to the tangent measure, and this uniform in j. And for that, the proof is, well, we didn't find another proof, maybe it's very well known, but we didn't find it. We are going back to Price proof of existence of tangent measure, and then with a very minor modification of the proof, you can get this kind of temperate estimates for the sequence of measure in that case. Okay, well, actually, I don't even know it is 50 or 1 hour, but maybe we'll see it's 45. Well, I can put another, well, no, I'll stop here. Okay, thank you for your attention.
Well, thank you very much. You still have time if you want to take.
Okay, if you insist. Okay, let's go for it. So these are extra slides. Because, well, it is natural when you introduce a wavefront set. Well, you first have elliptic results, but also you have, you might ask about propagation of singularities, right? And in this direction, we don't have too many results. We tried a bit. Well, you have something for transport equation, okay, for measure with the values, vectorial values. And the nice part is that, well, if you just take a scalar diagonal operator, A, then what you can see is that, well, in X, you will be evolved by what is expected from the propagation of singularity theory, meaning that you'll evolve by the gradient in psi of the principal symbol of your operator. So in this case, it is precisely B. So in X, you have the expected motion, and on the polarization part, you also have this propagation, and it involves only the coupling part H here. Okay, so, but this can be proved really by hand, just solving the equation. So now what is more interesting is that we manage also to do a propagation of singularities where the principal part of the equation is not diagonal. I mean, not identity times an operator. Okay, so it says typically if you have an equation like this, it says that again in X you have the expected motions. Okay, actually it happens that you can decouple completely the evolution, the equation for the singular part of mu1 and mu2. Okay, and then the polarization evolves just in terms of the principal diagonal coupling, I mean coefficient in the equation. Okay, and this to prove this, you have to use some microanalysis too. So you can do it just by hand. So now 50 minutes, I think it's more than enough. Thank you very much for your attention.